Swayam Prabha. Digital India. Educated India.
All right, good morning, good afternoon. Welcome back to the series of lectures on analysis and design of rigid pavements. We are in module 4, which is the last module of this series of lectures, and module 4 is on the mechanistic empirical design of rigid pavements. Let's take a brief moment to remember where we are in the class, how we got all the way here to module 4. So, module 1 was a brief introduction. In module 1, I basically told you about the 4 major types of rigid pavements, that is jointed plain concrete pavements, JPCP, jointed reinforced concrete pavements, JRCP, continuously reinforced concrete pavements, CRCP, and pre-stressed concrete pavements, PCP. Of these, JPCP is by far the most commonly used type of rigid pavement, and so in our discussion, we have largely been talking about JPCP. CRCP is also used, it's not as commonly used as JPCP, but you'll find many examples of it. So, CRCP is used, but we have not talked about it explicitly till this point because the analysis of CRCP actually tracks very closely with the analysis of JPCP. There are only a couple of minor variations here and there. The design of CRCP does have some notable differences from the design of JPCP, which obviously you might expect because they're such wildly different types of systems. And in today's lecture, actually for the first time, we will deviate between JPCP and CRCP. Now, JRCP is very rarely used. We really didn't talk about it in the class because you'll almost find no example where it's used. And then you've got PCP, which is a very specialized application. It might be used on airport runways, for example. So because it's so specialized, I decided not to discuss it in this class. Now, modules 2 and 3 were about the analysis. So the course is on analysis and design, but as I established in the previous lecture, at least the modern mechanistic empirical design is essentially an iterative analysis. So before we do the design, we have to be very good in terms of doing analysis. So we saw that there were broadly 2 categories of analysis methods of rigid pavements: the classical methods and the modern numerical methods, generally the finite element method. So the classical methods are classical because they're old, but more importantly, they're old because they have certain closed form solutions. So some nice, easy formulas, not simple formulas, but formulas which we can calculate, for example, by hand if you want to. Formulas which you can calculate, for example, with a calculator, or we could put the numbers into a spreadsheet and do the calculation, but no sophisticated computer programming is required. We saw that, and we saw several examples of those methods. So it started from Westergaard almost 100 years ago. Then we moved on to see other methods, for example, modifications to Westergaard method, which various authors made. We saw the Freiberg method. We saw modifications from Tabtabe to the Freiberg method for analysis of a single dowel as well as a system of dowels. So those were all analytical methods. At the end of module 2, we saw that there were several limitations to using analytical methods. For example, in analytical methods, one major assumption was that slabs were large. In other words, wherever the load was placed, the other joints away from that load were very far away, such that they did not have an effect for the stress at that point. That's a very major assumption, and as we saw in subsequent lectures, it was not a very good assumption. And when slabs become more reasonably sized, then that assumption is no longer valid, and we can have a very significant deviation in stress and deflection because of that one assumption. Another assumption which was made in those classical methods was that loads are circular, and later there were some modifications made which allowed for loads to be square in the footprint. But in both cases, I showed you an example of a realistic looking tire imprint on the road, and we saw 2 things. A, it is by no means circular or square. It's quite irregular. It actually follows the tread of the tire and its particular shape. And furthermore, the pressure distribution on that footprint is not uniform. It was not a single pressure. Different points on the footprint had a different pressure. So those were 2 assumptions. There were certain other assumptions which we talked about. which are made by the classical methods, but which do not correspond to the actual physical reality which we observe. And that's why there was a need felt to have better classical methods techniques. Remember, as we talked about previously, design is iterative analysis. So every error we make in our analysis is also going to feed into our design. So we want, to the extent possible, we want accurate analysis methods. But what we saw is, in order to overcome the limitations which I just outlined, it was actually quite hard. So we saw that there was a partial differential equation, the Sophie-Germain equation, with an additional reaction coming for a Winkler foundation. That's the governing equation for JPCP. And as we saw, analytical solutions for it were difficult even if we made a lot of these simplifying assumptions. And that's why smart people like Westergaard created the solutions for us. But if we wanted to overcome these assumptions, it's very, very hard to impossible to come up with analytical solutions. So in the 1990s then, the thinking changed. The idea was, let's get a solution method where we give up on some amount of accuracy. We are willing to tolerate maybe 1%, maybe 5% of error. We are willing to tolerate some amount of error as long as we can overcome all these assumptions which are actually creating much larger errors in our analysis. And that came through the finite element method. So the basic sort of philosophical change with the adoption of the finite element method was that we gave up on the idea of trying to get analytical or exact solutions based on certain bad or poor assumptions. Instead, we wanted to relax those assumptions. We wanted better assumptions, but we were willing to tolerate some amount of small error in our solutions. Now, the finite element method is not new. We don't call it a classical method, but truly it is quite an old method by itself. The reason the finite element method became popular is because computers became popular, widely available, sophisticated, and able to solve fairly large problems. So when we went through the finite element method, we saw that one of the basic ideas in FEM is that we don't solve the solution everywhere. We solve the solution at some discrete points, and what we're solving for are called degrees of freedom. At those discrete points, we get an approximate solution. And in between those discrete points, we assume that the solution varies as some type of polynomial. It could be linear, it could be quadratic, etc. So we make those assumptions, and then we basically turn our partial differential equation, the Sophie-Germain equation, we convert that into a series of algebraic equations. Now, when I say series, I don't mean 2 or 3 equations that you can solve by hand. It can be thousands, it can be tens of thousands, hundreds of thousands of equations which have to be simultaneously solved. Obviously, we're not going to do it by hand. So the challenge with the finite element method is it has to be implemented on a computer. For any practical problem, it needs to be implemented on a computer, for which a fair amount of sophisticated programming is required. The good part, however, is many smart people have come up with several programs, some general purpose, some designed specifically for JPCP, such as IceLab, which we looked at in a previous lecture. They have come up with these programs where we can very easily set up the problem. They've done all the back-end work, and we quickly get a solution. Now, of course, with any computer solution, we have to be careful. We should not accept it at face value. We need to check, has our solution converged? Is our solution reasonable? Does our solution look correct based on our experience? We need to question the solution, but the solution method can be implemented behind a computer. It's not very important for you to know every detail of how it's implemented. Of course, it's important to have an overall understanding. So we concluded module 3 with some examples of using the finite element method to solve a variety of cases, and we saw that we could solve a very large number of degrees of freedom in less than 1 second using IceLab, for example. When we came to module 4 in that case, so we had 2 previous lectures in module 4. In module 4, I emphasized that design is iterative analysis. So in analysis, we are given everything. We know what is the pavement, we know its thickness, we know its geometry, we know what materials it's made of, or at least we can make a good assumption of what materials it's made of. We know what subgrade it's on. We know the type of load, climate load or vehicle load that it's subject to. We know all the inputs. We have to calculate the stress, and from the stress, we have to calculate some measure of performance. That is analysis. Now, design is very different in the sense that in design, when we are trying to design something, we don't actually have it. So when we are designing a JPCP, we don't actually have a JPCP yet. That's why we're designing it. So we don't have a thickness. We don't know what material it's made of. We don't know what traffic is on it because there's no road. We don't know the subgrade, again, because there's no road. We don't know climate, etc. We basically don't know anything about the inputs. Yet somehow we have to calculate a performance, and all we know is that the performance has to match some desired performance. So if, for example, our performance measure is stress, although it is not stress for JPCP, but if our performance measure is stress, we know that the stress has to be less than some strength. That's all we know. What loads do we apply? How do we calculate the stresses? Those are all up to us. So design and analysis are very different in terms of the procedure that we're following. In lectures 23 and 24 then, lecture 23, I gave you an introduction to how the answers to these questions, that is, how do we choose what type of loading we have? How do we choose what is an acceptable design? How do we do these calculations for what performance would be? The answers to these basically give rise in pavement engineering, but also in other applications. They give rise to three types of the pavement design philosophies: empirical, mechanistic. These are the two extremes. So in empirical meaning based on experience, we completely base our design on some large scale experiments which were conducted in the past. We build some statistical correlations along the way, and for the statistical correlations then, based on our new pavement that we're trying to design, either we use whatever data was available, or we have to extrapolate from that empirical data or that experimental data and come up with an experimental design. That was empirical. Mechanistic design, on the other hand, the idea is we are not going to conduct any large scale experiments. We may have to conduct small lab scale experiments, but not large scale experiments. So we take these lab scale experiments and we develop a mathematical model based on, which is basically a partial differential equation or a set of partial differential equations. We develop a mathematical model based on a set of partial differential equations, which we believe completely explains the behavior of our JPCP. So we come up with that, we apply whatever loads, etc. we want, and we calculate cracking, faulting, IRI, etc. Whatever else we're interested in, we do all of that purely through mechanics. Now, that's not to say we don't use the finite element method. Actually, we use it all the time. So we're not trying to calculate exactly. We are willing to tolerate some amount of approximation on the way, but that's basically what a purely mechanistic method does. No large-scale testing. You solve a lot of the partial differential equations using the finite element method, and you come up with an acceptable design. As we saw that in reality, doing that is easier said than done. Just creating a finite element model for a linear elastic plate, which was the point of module 3, as well as a finite element model for linear elastic dowels. Just doing that much, I'm sure, made a lot of you sweat. Now, if you had to do it for a non-linear phenomenon such as faulting, such as cracking, such as IRI, these are all non-linear phenomenon. Linear elastic mechanics cannot model these phenomena. If you had to do it for a non-linear phenomenon, most of you would raise your hands and give up. And most practicing engineers would not have the sufficient sophisticated level of training required to be able to develop and run such models. So mechanistic design is good for research applications. It has not made its way into practice yet for those reasons. So then we have mechanistic empirical design, which is a compromise between these two. The principle of mechanistic empirical design is we are going to use linear elastic mechanics to calculate the response of our system. That is, we will build our partial differential equations based on the assumption that our system is linear elastic. Again, I emphasize, the moment you assume you have a linear elastic system, you cannot model cracks, you cannot model faulting, which is ultimately what we're concerned about. So you see, there's a large assumption being made in this process. So we assume that the system is linear elastic. We calculate its stresses, we calculate its strains, we calculate its displacements. We know how to do these, for example, using the finite element method on the Sophie-Germain equation. We do these calculations, that's the mechanistic step. And then we might use fatigue theory, which is what we learned in the last lecture. We might use fatigue theory then to calculate fatigue damage. We calculate fatigue damage for a given load and a combination of load and climate. We calculate a given amount of fatigue damage. Okay, so then we get a term which I introduced in the last lecture, CFD, cumulative fatigue damage. So we can calculate some cumulative fatigue damage. This is all still mechanistic. We don't have a crack yet on the pavement. That is then when, if we want to actually model a crack or faulting or any other distress on the pavement, then we give up on the idea of doing it mechanistically because it requires fairly complicated non-linear mechanics. Instead, we take this fatigue damage term and we somehow empirically converted into cracking or faulting or whatever other term we are interested in. So the function, the empirical functions which convert our fatigue damage, which is a mechanistic term. So the fatigue damage is a mechanistic value which you can calculate using various programs, using various numerical tools. This fatigue damage then can be converted into cracking, faulting, or any other distress using an empirical function. Those functions are called transfer functions. And the topic of today's lecture, after that long introduction, the topic of today's lecture is basically to see what are transfer functions, how do we, so today's lecture is to explain the need for transfer functions, list the different steps developed to develop transfer functions. And there's no unique transfer function. There are actually hundreds of transfer functions. They're empirical in nature, and we'll see that that leads to many different forms of transfer functions. And we will actually list and look at several transfer functions for JPCP and CRCP. So this is the first time in the series of lectures where we are actually going to split between JPCP and CRCP, because we model them for different type of distresses. I'll give you a recap on that in a couple of slides. We model JPCP and CRCP for different distresses. And so because transfer functions are basically taking us from the fatigue damage to a distress, since JPCP and CRCP have different distresses, they have different transfer functions. So for the first time in this lecture, we are going to deviate between JPCP and CRCP. Okay, so just to put a little mathematical juice in what I just described in the introduction. So if you recall, in fatigue damage, we use fatigue theory to model rigid pavements. We talked about in the previous lecture, and please review the previous lecture if you want more details, but we talked about in the previous lecture how LRFT cannot be load and resistance factor design, which is used in structural engineering. It cannot be used in pavement engineering. If it's used in pavement engineering, it will give us the nonsensical result that the pavement should never develop any cracking and any type of distresses, which is not what we see in practice. So instead, we introduce the concept of fatigue theory, where the idea is that each load application has a very, very small stress. So the stress ratio is relatively small. It's less than 1. It's much less than 1. So when you have this small amount of stress which is applied, as such, you don't have any large amount of cracking developing, but you have a lot of micro cracks developing. So you have small cracks which are developing throughout the material. Over time, as you apply these small loads hundreds of thousands or millions of times, those small cracks start coalescing together and form a large crack. And that's then the final crack that we observe in terms of transverse cracking or longitudinal cracking. So fatigue theory then tells us the main outcome of fatigue theory is that for each stress applied, or each stress ratio, if you divide it by the strength, for each stress ratio, which is a combination of vehicles as well as climatic load. So you could have some temperature also, which would create some amount of, that would change the stress state. And of course, you have some loading from a vehicular load. So for each stress ratio which is applied, we actually develop in fatigue theory, we develop what we called an SN curve. An SN curve was a relationship between the stress ratio and the logarithm, not to forget, it's a semi-log curve. It's a relationship between the stress ratio and the logarithm of the number of load applications to failure, which in design terms, we can also call the number of allowable repetitions of that stress ratio. And generally, the curve looked something like this. So it had a negative slope. So as my stress ratio increased, my allowable number of repetitions decreased. That means if I have heavier loads, I can only have fewer repetitions of the heavier loads before failure. Recall here, failure was a little bit of a subjective term. So we have different SN curves. There are many differences between different SN curves. One difference is on the criteria of failure. We also learned of something called a endurance limit, that below a certain value. So if your stress ratio goes below a certain value, we say that we can allow an infinite number of repetitions. So basically, no damage there is no amount of damage which is being accumulated as a result. Some SN curves or some fatigue models have endurance limits, some don't. So the Indian practice is to have an endurance limit. The US practice is to not have an endurance limit for rigid pavements. So what we saw is that for a given load and a combination of load and climate, we saw that we can get a stress ratio. We calculate the stress ratio by calculating the stress. This has to be done generally using the finite element method. That's how it's done in practice, and divided by the strength of the material, the flexural strength, which is sort of a material property. It's not exactly, but for this class, you can assume that it's a material property. So for each SR, we can calculate NF. So if you have a given SR, we can calculate NF using this equation. That's going to give us the number of allowable repetitions to failure. So we have the number of allowable repetitions, but we also have a number of actual repetitions to failure. And that information actually comes from a combination of climate characterization and traffic characterization. Those will be topics which we will cover in subsequent lectures. But we can calculate a value which we call the fatigue damage, FT, which is the ratio of the actual number of repetitions, lowercase n, to the allowable number of repetitions. And then if we take the summation of N over NF, if we take the sum of the fatigue damage, so fatigue damage is for one combination of load and climate. If we sum up the fatigue damage over all combinations of loads and all combinations of climates, then that number we get is called cumulative fatigue damage, CFD. In some applications, it is also called fatigue, let me write it down, it is called fatigue life consumed. So cumulative fatigue damage, accumulated fatigue damage, fatigue life consumed. They all generally mean the same thing. Now, that we saw this in the previous lecture. We left the last lecture with something called Miner's hypothesis. So we can calculate fatigue damage. Okay, so given a particular load, given a particular climate, for a given JPCP, using finite element methods, we can calculate stress ratio. Combine the stress ratio with the SN curve, we can calculate NF, the allowable repetitions to failure. Given some information about the traffic, we can calculate what is the fatigue damage. Given a history of traffic and a history of climate, we can calculate the cumulative fatigue damage. So all of these things we can sit and calculate. The question is, when has the pavement failed? What is the point of the calculation if we can't design? And for design, we have to say when the pavement has failed. So in the previous lecture, I showed you, we concluded by talking about the fact that there are two failure criteria in fatigue theory which we can use. One failure criteria is a mechanistic criteria, and there are several criteria over there. The most common is called Miner's hypothesis. And Miner's hypothesis says that when the cumulative fatigue damage becomes 1, then we say the pavement has failed. So when CFD is exactly equal to 1, that's what we call failure. That's a mechanistic approach. Now, to bring it to today's discussion, what does it even mean to fail? So if we say that failure is when CFD is equal to 1, from physically, what does that actually mean? Can we see it? So if I ask you today to go out to any rigid pavement near your house, look at it and tell me, oh, what is the fatigue damage? Is it 1? Is it less than 1? Can you do that? You actually can't. You can't see it. Can I take out a scale? Can I put a ruler, or could I get a thermometer or something? And can I measure the fatigue damage in the field? No, not really. What can we measure, however, when we go out in the field? We can measure cracking. And if you go back to module 1 in our lecture 4, which is part of module 1, we did talk about how cracking can be quantified and how it's measured. We could measure faulting, we could measure IRI, for example, and other measures. These are things that we can actually measure. These are things which are real, so to say. Fatigue damage is a mathematical concept. We could use failure based on fatigue damage. Indeed, as we shall see, the Indian practice is to actually use a fatigue damage mechanistic criteria for failure. So we could use a mechanistic criteria for failure in terms of CFD, where CFD is equal to 1 as per Miner's hypothesis, but it's not very satisfactory. As an engineer, it doesn't really help us to say that the fatigue damage is 0.8 or 0.6. What we would like to say is that if I have 100 slabs, so let's say I have 100 kilometers worth of slabs, how many of those slabs have developed cracking? Similarly, how many of those cracks have developed faulting? How much faulting is there? Is it a little bit of faulting? Is it a lot of faulting? What is the IRI of this 100 kilometers? As a pavement engineer, I actually would like these answers. I would like to know these quantifiable values because it's what I can relate to. So this is why, while Miner's hypothesis provides a useful criteria, I'm not saying it's not particularly useful. Again, in the Indian practice, as we shall see when we get to IRS 58, we actually use Miner's hypothesis. So while Miner's hypothesis certainly provides a useful mechanistic failure criterion, as pavement engineers, it does not mean too much for us. It's not physically relevant. It doesn't really help us in our work. We would much rather express failure in terms of distresses. Because after all, as pavement engineers, when the public, and most roads are built by a government and so they are public infrastructure, When the public complains, they don't call you and say, my fatigue damage has become 0.8, do something. That's not what you hear. What you hear is, the road is cracked. The road has a lot of faulting. The road is very rough. These are the complaints you hear. So you would like to quantify your performance based on these values, these distresses, rather than on a sort of mathematical abstract term, which is what fatigue damage is. So how do we calculate distresses? How do we then go from a fatigue damage, which we can calculate? We can definitely calculate fatigue damage. How do we go from fatigue damage to actual distresses? In other words, if I say I have a fatigue damage, let's say a fatigue damage of 0.5, just as an example. If I have a fatigue damage of 0.5, then how do I know what is the percentage of slabs which are cracked? So let's say in 100 kilometers, if I have, let's say I have 100 JPCP slabs, how many of those slabs are cracked? How can I relate these two? I would like to relate these two for reasons I just explained. How can I do it? Here again, there are two methods to do it: mechanistic and empirical. So we could do it mechanistically. In the sense, we can use nonlinear mechanics. Since we have fatigue damage, we basically have stress. If we have stress, then maybe we can calculate damage, we can calculate some cohesive zone mechanism, etc. There are many different ways to do it. These are non-linear mechanics methods. They are quite complicated. They are used in research. You'll find some research papers which do this. In particular, surprisingly, in mechanical engineering, you'll find quite a lot of this. So you will find a lot of research papers about it, but in practice in pavement engineering world over, this is too complicated. This approach is generally not used. Instead, what we use is an empirical method. The empirical method basically gives us a simple empirical, and empirical again meaning statistical relationship. That is, it tells us, let's say fatigue cracking, I call this FC. Fatigue cracking naturally as a percentage. This is percentage of slabs which are cracked within a certain length of interest. The fatigue cracking is some function. We'll see what the function is. It is some function of fatigue damage, and this function is derived by using simple correlations. So we just use simple statistical techniques to derive this function. Advantage, it's pretty straightforward. We have the data, we fit the data, that gives us a relationship. The problem is our data. We need a lot of data. So in order to develop these empirical functions for fatigue damage, we actually have to collect a lot of data about pavement performance. Okay, so recall that this is the overall flow chart for mechanistic empirical design. This, by the way, will keep coming back as we go through module 4. This particular slide will keep coming back again and again. So this is the flow chart for mechanistic empirical design. We start with some inputs, but most importantly, we have a trial structure. We take our trial structure, we calculate our structural responses, stresses, strains, and displacements. We calculate that using linear elastic mechanics. We cannot calculate cracking and faulting and etc. using linear elastic mechanics. So we calculate it using linear elastic mechanics, and then from there we get a fatigue damage. We convert that fatigue damage into some distress, and the correlation we use, the empirical correlation we use to do that. So this particular function F, the empirical correlation between fatigue damage and distress, is called a transfer function. So that's a new terminology which you're hearing. Transfer function transfers fatigue damage to any distress. And it is an empirical function. It has been determined empirically. And from there, from the transfer function, we add some reliability information, and then we calculate performance. We compare performance to some criteria, and then we do an iteration around it. So this we already saw in a previous lecture. So to give you a formal definition, a transfer function is an empirical function. I remind you again, empirical function means it's based on data collected through large-scale experiments. That's what we mean by empirical in this context. So a transfer function is an empirical function that correlates a mechanistic response of a JPCP, which could be stress, strain, deflection, fatigue damage, etc. These are mechanistic responses. A transfer function is an empirical function which correlates these mechanistic responses with observed distresses that we see when we go out in the field and we collect this data. So you cannot build a transfer function sitting inside an office. You have to go outside, you have to collect the data, and you have to know quite a bit about the history of the pavement. And based on that, you have to develop these transfer functions. These transfer functions are empirical, and this is actually the empirical part of ME design. So ME, recall, stood for mechanistic empirical. And now I can formally give you the definition of mechanistic empirical. We have enough background. The mechanistic part for JPCP is calculation of fatigue damage. The empirical part is the calculation of distresses. This is what mechanistic empirical design means. Okay. Now, since transfer functions are empirical, so empirical basically means you're applying some statistical correlations. Any number of possibilities exist on what the functional form will be. There are so many different ways to statistically fit data to a variety of curves. We'll see certain examples of them as we go by. But what you want to understand is these transfer functions are not unique. The transfer function itself, first of all, greatly depends on the underlying data. So for example, if we went all over India and collected data for a very large number of roads across the country on the amount of cracking, and somehow if you could relate it to fatigue damage, we'll talk about that in a little bit later. But if we collected this data from all over India and developed this correlation, we would get one answer. If we did it, let's say, only within a particular state or within a particular district, and then we did this correlation, we would get another answer. If we use correlation using one method, we'll get one answer. Using another method, we'll get another answer. So there are a very large number of transfer functions which you will find in literature. Which transfer function to use really depends on what your application is and how much error you're willing to tolerate. Because, for example, if you are collecting data from all over India using the transfer function and you're only designing a road in Kerala, you might not, your data does not represent conditions in Kerala alone. It represents conditions all over India. So you're not getting exact behavior of the pavement as it would be in Kerala because you are adding data from other sources as well. So there is some amount of error which will come. And so if you are very interested in reducing the error, maybe you should build a transfer function for your particular application, which is easier said than done. So let's look at what a commonly used transfer function. This is actually a transfer function which AASHTO uses. That's why I'm showing you this. A commonly used transfer function for fatigue cracking. Now, fatigue cracking is defined as the percentage of slabs with a transverse crack. So if I have 100 slabs or 1,000 slabs over a section, I conduct a survey and I see how many of them have developed a transverse crack. It could be a low severity, high severity. In this case, those are not differentiated between. So both low severity and high severity are considered cracks. So if we actually measure it, then we get the percentage of fatigue cracking. So percentage of fatigue cracking is defined as the percentage of slabs which have developed a transverse crack within some representative section. And a relationship between fatigue cracking and fatigue damage, which is our transfer function, this is what the one used by AASHTO, is the one which I'm showed over here. So FC as a percentage is 100, the 100 is because of the percentage, divided by 1 plus C1 into FT raised to the power of minus C2, where C1, C2, which are greater than 1, are some empirical coefficients, they are regression coefficients. This relates fatigue damage with the fatigue cracking. So particularly, as I said, AASHTO uses this functional form, and then within AASHTO itself, and we'll see more details about AASHTO in a couple of lectures from now, but within AASHTO itself, you have a large number of transfer functions. Again, the C1 and C2 have to be fitted based on your data. If you're using national data, you'll get some values. If you're using state data, you'll get some values. District data, some values. So there are a whole variety of ways. There are different fitting techniques also. They'll also give different values. This is the particular functional form which AASHTO uses. So FC as a percentage is 100 divided by 1 plus 1 into FD. So C1 is equal to 1 raised to the power of minus 1.98. So C2 is equal to 1.98, almost 2, but not quite 2. If I actually plotted this function over here. So I have FD on the x-axis. It goes from 0 to 1. By the way, FD can exceed 1. If you believe failure is that FD is equal to 1, that's one thing. But if you don't believe FD is equal to 1 is failure, that is, you don't follow Minor's hypothesis, then that's also equally valid. It just depends what theory you're using to define failure. So what I see over here at FD is equal to 1, I actually have a fatigue cracking of approximately 50%. What that is saying is that if I have a pavement where somehow I could say the fatigue damage is equal to 1, or the cumulative fatigue damage is equal to 1, what that means as per this function, as per this empirical correlation, it means that 50% of my slabs are cracked. Now ask yourself the question, is this acceptable? So imagine yourself driving on a road. You'll be driving 10, 20, how many ever kilometers, and it's a JPCP road, and every alternate slab has a crack. So you're experiencing a little bit of bump, a little bit of shaking with every single slab that you're going over. You will agree with me, that's not a very comfortable phenomenon. So really, in this case, we do not actually want FD to reach 1. If FD reaches 1, our road has become such a bad condition that it's not safe anymore to drive on it. What is safe? Maybe we are okay with 20% fatigue cracking. Maybe if it's a small local road, even we could go up to 30%. I'm doing the wrong value. Maybe we'll be okay with 20% fatigue cracking. If it's a local road, maybe we'll be okay with 30% fatigue cracking. If it's an expressway, maybe we want no more than 5%. So based on these limits, based on the limit of fatigue cracking, this gives us our failure criteria. So the failure criteria is actually a policy criteria. If it's a small local road, maybe you're willing to tolerate a high amount of cracking. If it's a major expressway, you are not at all willing to tolerate even a small amount of cracking. So the limits of performance really come from a policy perspective. It is much easier to set a policy on cracking than fatigue damage, because fatigue damage is just a mathematical term. Cracking is something we can see, measure, and which people can complain about. Okay, so how do we develop a transfer function? It's much harder than you think. And I should add, in India, we don't actually have any good transfer functions because we simply haven't, it simply hasn't been made as of yet. So it's a fairly complicated process to create a transfer function. Here are the general steps. So we take a section of a road. What is a section of a road? It's whatever you are interested in. It could be 100 kilometers of a highway within a state. It could be all the MDRs, major district roads, inside a district. It doesn't matter. We take a certain section of road or a representative sample. We need to survey it at regular intervals. For example, every 2 years. By the way, this is already done in many parts of India. Wherever we have toll roads are usually surveyed regularly for distresses. Because if it's a performance-based toll contract, then the distresses also determine how much money the concessionaire makes. So it's not unusual to do these distress surveys. 2 years is actually quite a long frequency. It might even be done every 6 months. So at every interval, which could be 2 years or every 6 months, whatever, at every interval, we must measure the amount of distresses. If it's cracking, for example, we have to say what is the percentage of slabs cracked. If it's faulting, what is the depth of faulting? If it's IRI, then what is the IRI, etc. So at these regular intervals, 6 months, 2 years, whatever, we have to go around, measure what the cracking is. After that, we have to go back and look at the records and see that in those 2 years or 6 months, whatever that period was, what was the climate, what was the traffic condition, pavement and material structure, of course, must be known. That will be known from when it was constructed. We must know these properties, and then we have to calculate that for that particular road, in the last 6 months or 2 years, this was the sort of climate it was subjected to, this was the traffic it was subjected to, this is the type of pavement materials and structure that we have. From that, we can calculate the fatigue damage, and from there we can get the cumulative fatigue damage, which in short, I'm not going to repeat it, we've already done this. We calculate the critical stress using finite element method, most likely. You calculate the critical stress, you get the allowable number of, you get the stress ratio from the critical stress, you get NF, which is the allowable number of repetitions. From your traffic information, you get fatigue damage. Over all the climate conditions, over all the loads, you sum up your fatigue conditions and you get your cumulative fatigue damage. So now what we have is, over that period of measurement, so every 2 years or every 6 months, whatever the policy is, we now have calculated mathematically what is the fatigue damage, and we have done a site survey and calculated the quantity of distress, for example, percentage of cracking. And then we develop a statistical correlation between them. There are many methods to develop a statistical correlation. Most of you are probably familiar with linear regression, and it has been used in many cases. There are also various non-linear regression techniques. There are certain semi-analytical techniques. So what semi-analytical means is that we have some type of physics-based model, but the physics-based model contains some empirical coefficients inside. So little bit of physics, little bit of empiricism is built into it. That's what we call a semi-analytical method. Of late, you'll find a lot of papers in literature where they've also tried to use machine learning, for example, to develop these models. So as long as we have this data, the data is fatigue damage, and for example, if you're doing it for cracking, fatigue cracking. This much fatigue damage, this much cracking. Another amount, another cracking. As long as we have this data, we build some correlation, and that final correlation, that statistical relationship we get is called a transfer function. So it's not easy to develop these transfer functions. You have to know a lot about climate, you have to know a lot about traffic, you have to do regular surveys and quantify what the distress is. But given all this data, it is possible to develop a transfer function, and there are many techniques to develop these transfer functions. One more thing I want to point out about developing these transfer functions. So generally in the US, they have a lot of transfer functions, a lot of work is done on it. When we collect this data for transfer functions, generally we do it on in-service roads. That is, we take the survey of roads on which regular traffic is already moving. Now, the problem with in-service roads is we have to ask ourselves what range of transfer functions are valid. So to give you an illustration, let's look at this figure. On the x-axis is the predicted cracking and the y-axis is actual cracking. So the predicted cracking, for example, is coming from a transfer function. And the actual cracking is whatever was measured. So we fit some amount of data to this. So here we see the R squared is 0.86, not bad. This is telling us that our transfer function is good. It's reasonably good. It's predicting 86% of the variability. Okay, but let's take a look at where the points are. You will see here that if I just limit the data to 20%, so within the range of 20% cracking, there's a lot of data. Outside of it, not much data, much less data. So you want to notice that beyond 20% cracking, there's not much data. Why? Well, as I mentioned, this is data collected from an in-service pavement. So maybe this is a highway. If you're seeing 20% cracking, people are complaining about it. There might be a policy that some amount of rehabilitation, some amount of techniques for maintenance have to be done once you reach 20% cracking, which means that you actually don't have the opportunity to develop a transfer function where the cracking is actually going from 0 to 100, simply because you don't have that data if you're using in-service payments. So one challenge with developing transfer functions is we want them to be valid from 0% cracking to 100% cracking. But the data which we have, it's very difficult to get data which goes beyond 20 to 30% of cracking. So we are basically doing a lot of extrapolation if we have higher percentage of cracking. That's one issue with transfer function. So how do we overcome this? Well, we're not going to overcome it for any existing in-service roads because generally you can't have a very high amount of cracking. It becomes unsafe for drivers. There is an alternative technique which is called accelerated pavement testing, or APT. So this is an example of what's called a heavy vehicle simulator. This is in CRRI in New Delhi. I got it from the website link down there. What this basically is you have a road, a test section. So this is not an in-service highway or in-service road. This is a test section that has been custom built. It's an experiment which is being conducted somewhere on a test site. And on that, this heavy vehicle simulator is placed. What this HVS is, as the name suggests, it's a heavy vehicle. So basically, it's a tire. It's a very big, heavy wheel, much heavier than typical wheels. And that's why we call it accelerated pavement testing. So you're not applying small loads. You actually want to get very high amounts of fatigue damage. So instead of having many repetitions of small fatigue damage, you want a small number of repetitions of high fatigue damage. So this wheel, it's actually, you can see it here. This is the wheel over here. This wheel just goes back and forth for hours, for days, tens of thousands of repetitions. During that time, this section has been instrumented. You can measure the strains, you can measure the stresses, you can measure the cracking. A lot of data can be collected over here. And so what we have is, we have a section where we are actually purposely, we are putting a very high amount of damage. Because no real traffic is going on this, it's just a test section. Because no real amount of traffic is going on this, we can go to cracking of 60, 70, 80, 90%. We can really crack this pavement completely under this heavy load. And because it's a particularly heavy load, we can do it through accelerated pavement testing. So a well-designed in-service rigid pavement should not show a very high amount of cracking for maybe 20, 30 years. This accelerated one, within a month, you might be able to crack the whole thing because you're putting such a heavy weight. And that's on purpose, is so that we can collect data very quickly. We don't have to wait 30 years to collect data. Within a month, we can collect a large amount of data and then build some custom transfer functions. So that's basically one way to get over this issue, that in-service payments will not give us data over the entire range of cracking. So these APT techniques can give us data for the entire range of testing. Okay, so that was one transfer function. So we've looked at a lot on cracking. I had mentioned briefly that over here, I can bring up the slide. I mentioned this semi-analytical method. So I wanted to give you an example on semi-analytical methods. So an example of a semi-analytical transfer function is actually used for faulting. Let's recall what is faulting. So faulting is basically, again, I have an approach slab and I have a leaf slab. In this approach slab and leaf slab, my idea is that when there is no load, these two should be at exactly the same height. When there is a load, obviously I'm going to have some amount of deflection, that the approach slab is going to deflect by some WA, the leaf slab is going to deflect by some WS. So this is the leaf slab. The concept of faulting is that over time, this deflection is no longer elastic, that some amount of plastic deformation has happened, so that even when I don't have a load, I have some amount of differential deflection. So I have a built-in difference between the approach slab and the leaf slab. This amount of difference, this differential deflection, is what we call faulting. That's just a reminder of what is faulting. So faulting is related to differential deflection between the leaf slab and the approach slab. The transfer function for faulting, there are many transfer functions for faulting. One of the popular transfer functions of faulting, which is what ASHTO uses, is a semi-analytical one. It's based on the following idea. Let's say that we have a slab, and remember, faulting is going to happen at the edge. So I've applied a load over here, and let's say the load is applied over a certain area. What exactly that area is something that's something you have to choose. That's something the designer has to choose. We'll talk a little bit about designing a transfer function towards the end of today's lecture. But let's say I choose some amount of small area and I apply a load. I know I'm going to get some amount of deflection. If I take that deflection and I multiply it by the, if I take that deflection and I multiply it by the coefficient of subgrade reaction, then that is giving me the reaction force. So the subgrade is being pushed by some deflection W, and it is then reacting with some amount of force. The work done by that force, in that case, the work done by the load, is the force into the displacement, or the differential energy. So the energy which is created by that work, or which balances the work done. The deformation energy in that case is kW square. So it's kW, which is the force, into W, which is the displacement. So force into displacement, kW square, summed over this particular area of interest, whatever that area of interest might be. So when we have this approach slab and when we have a leaf slab and we have a load which is applied over here, we are going to get some deflection in the approach slab in a corresponding area on the leaf slab side, which is not loaded. So the load is only here. On the corresponding area on the leaf slab side, we will also get some amount of deflection energy. So we get some summation of kWA square here, and we'll get summation of kWL square on the leaf slab side. The difference between these two is called the differential energy, or the DE. And that is given by this equation over here, summation K WA square minus WL square. Now let's ask our question. What is the value of the differential energy if we have 100% load transfer? Recall, go back to the lecture on load transfer. 100% load transfer means WA is equal to WL. So WL. So if I plug into this formula over here, the differential energy is 0. So if I actually have a well-performing pavement with 100% load transfer, that 100% load transfer almost never happens, it's an ideal condition, then my differential energy is 0. On the other hand, suppose I have 0% load transfer, which is the worst possible condition. At 0% load transfer, WL is equal to 0. So if WL is equal to 0, that maximizes my differential energy. So what you see is differential energy is actually a measure of what is the amount of load transfer which is happening. And over time, if my differential energy is very large, then I start getting plastic deformations. And so the difference between the elevation of the approach slab and the leaf slab starts becoming permanent. And that permanent deformation is what we call faulting. So what we can see is, if we want to develop a particular mechanistic model or a mechanistic empirical transfer function for faulting, it would be a good idea that it's somehow related to the accumulated differential energy. So how much differential energy is being accumulated over time with every cycle of vehicle which is passing over it. That's a physics-based logic. So this differential energy is a physics-based term, which you see clearly. And our idea is maybe our faulting should somehow be related to the differential energy. That somehow is the empirical part of the transfer function. So what ASTRO does is it provides these equations. I'll explain the equations in a second. It uses an incremental faulting model for transfer functions for faulting. What it basically says is that the change in faulting at a given time step I, that time step could be every hour, it could be every month, it could be every day, whatever. It's incremented in the sense that we are slowly building up the amount of faulting. So we are calculating the amount of faulting not at the end of the service life, but at periodic periods, 1 day, 1 month, etc., during the service life. So it says here is that the change in faulting is equal to some maximum faulting minus some previous faulting into the differential energy, square into the differential energy. So you see this differential energy term is come over here, where the maximum faulting is again related to the differential energy. What you will see here is we have a C34, C5, C7, C12. You see a number of these C's, there's C6 over here. These are empirical coefficients. These are calibration coefficients which come from regression. So differential energy is a physics-based model. So it's mechanistic, but these empirical coefficients, they have to be calibrated through data which is collected over time. So we have a physics-based term, differential energy. We also have a bunch of empirical coefficients. This is why we say that this particular transfer function is semi-analytical in nature. Are all transfer functions semi-analytical? No. The one I showed you for fatigue cracking, it was purely empirical in nature. It depends. You can have purely empirical, you can have semi-analytical. For the same thing, for example, for faulting, if you look in the literature, you'll find 10 other faulting models which are available. This is just the one from ASTRO which I'm showing you, but there are many other transfer functions which are available. So you have a large number of transfer functions. There's no such thing as a unique transfer functions. Okay. Now, one particular transfer function, the last one which I want to talk about, is actually about punch-outs in CRCP. I had promised that we are actually going to see a slight deviation in this lecture between JPCP and CRCP. So in JPCP, if I have a slab, for example, I'm very concerned when I get a transverse crack. In CRCP, I pointed out that we don't have slabs. We have one continuous concrete, which then naturally develops some very, very tight cracks along the way, roughly spaced 1 meter apart, if it's been designed properly. So we have these very tight cracks with very, very small widths, these hairline width cracks. Ideally, the cracks should be parallel to each other in the transverse direction. That's not a distress, that's exactly how it's supposed to behave. Because these cracks are so small, the width is so small, it's very smooth for drivers to drive on them, so we don't call them a distress. But sometimes the cracks don't follow parallel paths. So instead of being parallel, the crack might go something like this and eventually hit a particular slab like this. This is what we could call Y cracking. So we have one piece of slab which has now just come out. Or we could somehow develop, for some reason, we could start developing a longitudinal crack, in which case between two transverse cracks and the longitudinal crack, one piece of concrete is going to come out. And when I say come out, it literally comes out. It punches out, and that's why this type of distress is called a punch out. It does not occur for JPCP. It occurs and is a very serious problem for CRCP. So there are no JPCP punch out models because there's no punch outs in JPCP. Instead, there are CRCP models. Now, this particular example I have over here taken from TextDot, this is one particular transfer function which they developed for CRCP. Here the analysis, that is the calculation of damage, or what they call here is accumulated damage, that's the same as CFD as we learned previously. This CFD is calculated exactly how it was done for JPCP. Same approach. The steel in CRCP, we learn this several lectures later also, the steel in CRCP is not meant to add any strength. It's just meant to keep the crack width very small. So the technique we use to calculate the stress is the same technique we use for plain concrete, which is the same technique we use for JPCP. So we have our CFD here and we have punch outs per mile in this case because they're using those units. They collected this data. So this was calculated mathematically. This data was collected on the field and they fit some type of power law to it where they had an R square of around 0.68. Not very good, but actually many transfer functions will generally be of that order. Another transfer function which could be used for CRCP is for crack width. So I pointed out the CRCP works, you have regularly spaced cracks, but the width of the crack is so small, it's in microns, The width of the crack is so small that when a car drives over it, it's not experiencing a crack. As far as the car is concerned, it's just one smooth pavement. That's why we don't call these cracks as distresses. But the crack width then is very important. If the crack width gets too big, then suddenly it goes from being not a distress to being a distress. So we would ideally like to control and predict our crack width as part of our CRCP design. And so there are other models which I've pointed out over here, which tell you the CW is for crack width. It's taken from this paper down here. You're free to download. I think this is freely available. It's open source. So you're free to download this paper and look at it. But for now, just understand this is some particular model where you have some C2 over here, you have some CC over here. These are empirical coefficients. So the model has to fit the empirical coefficients, but this is how you can calculate crack width for CRCP. Okay, last towards the end, we're almost done for today's lecture. A few thoughts, just two slides, a few thoughts on developing transfer functions. I've been involved in developing transfer functions during research, and it's very easy to teach it. Unfortunately, when you do it, a lot more things come in which are difficult to explain on teaching. So I'll try my best to explain what these additional issues are. So truly speaking, developing a transfer function is not purely a scientific endeavor. That is, it's not just here is my data, now fit my data. It is also an art. Why is it an art? Because you wish your data was perfect. In truth, it's not. In some cases, as we saw, the data is not representative of the entire range of values. You have data for a small range of values, and now you have to use your judgment as an engineer to figure out what the data should look like in those parts where you don't have any data. For example, if I'm doing fatigue cracking, I might have data over here, so I can fit a curve over here. Outside of this, does the data look like this? Should it look like this? Should it look like this? That's a subjective decision. And that's something you have to make while developing a transfer function. So a lot of subjectivity comes into play in developing transfer functions. Furthermore, transfer functions also show policy considerations. What's an example of a policy consideration? Suppose the policy is that after 20% cracking, so I have a transfer function which is good for 20% cracking. As an agency, for example, NHAI or any other agency, as an agency, I have a policy that once I have 20% cracking, I don't want to wait more than a couple of months to do some rehabilitation. That could be a policy. It is ideal then that your transfer function maybe be of this type, that you show that after 20% cracking, you have a rapid increase in cracking. You don't have any data there to justify this, but you choose such a function because your policy tells you there's such a function. Or maybe your agency says that up to 50% cracking, I really don't care. So then you might choose this transfer function, where you just assume a gentle increase in fatigue cracking so that at the end of the service life, you can reach 50% cracking, because that's how the policy decision has been made. So transfer functions are not purely a mathematical exercise, they show policy considerations. There is one particular paper, Ionides, we've seen this author before. So it's a very interesting paper, very recently published in 2022 in a conference. You'll need to get to a university library to get access to this, but please try, it's a very well-written paper. The title is Reflections on the Use of Transfer Functions in Pavement Engineering. I won't go into all the details, but I just will quote one line from this, which I thought fully explains what I'm trying to say. It is concluded that the transfer function has always been a tool for implementing policy rather than a data-driven algorithm. So developing transfer functions has subjectivity. The policy of the agency will also be reflected inside the transfer function. Data alone cannot create a transfer function. Okay, so with that, we conclude today's lecture. So what we saw in the previous lectures, we saw an introduction to the philosophy of mechanistic empirical design. We looked at fatigue theory, which is a key aspect of mechanistic empirical design. And then we looked at transfer functions, which help us create some kind of failure criteria within the framework of ME design. So now we have all the tools necessary to look at an actual mechanistic empirical design procedure. And we are going to start by the US procedure, which in my opinion is the most sophisticated procedure in the world that exists today. That's why we're starting on it. And the one that the Indian procedure also is based on to a very large extent. So in the next lecture, we'll talk about that procedure, which is the Mechanistic Empirical Pavement Design Guide, or MEPDG, developed by AASHTO. So in the next lecture, we will go into the AASHTO MEPDG, give you an overview, and see how it works. Thank you.